I'm glad this thing is on, because the invariant that the light comes on when noise comes out has been broken at some stage. So, okay, thank you for having me. Very nice to be along. Very nice to talk about functional programming to a home crowd as well, because many of you might realise that Scotland is the home of functional programming. We fly the flag like this now because so many functional programming languages have grown out of Scotland. So Haskell in particular. So when Henry asked me to do this, he sent me the results of a survey on, so when you signed up you might have filled in a survey on what you know, what your background was, and I got some information out of it. One is that not many of you do functional programming for a living. Is that a reasonable expectation? Some of you have heard of Haskell, some of you have even used Haskell. There's some people hiding. Okay. For this talk I'm going to talk about another language that's come out of Scotland, of my own, called Idris. It is a functional programming language. If you haven't seen any Haskell before, it should look familiar to you. If you've seen something NL derived before, it should look familiar to you. If you haven't, I'll walk you through little bits of the syntax, so I'll try to give you some idea of what's going on as we go, and I'll try to at least motivate, why I think languages with strong type systems are important and useful for the future. I was originally going to call this type-driven software verification, but I was told that wasn't clickbaity enough, so we're now going with type-driven development. And the thing I like about calling it type-driven development is that it has the abbreviation TDD, just for maximal confusion or annoyance. Okay, so I'm going to talk about Idris. I like to describe Idris as a Pac-Man complete functional programming language. If you look at a lot of the modern experimental academic languages, people like to do very complicated things with them, but struggle to write Hello World, or struggle to do any kind of interaction with graphic systems, or anything that you might want to do in realistic programming. So one of my goals for the design of Idris is to have it something that you really can write, I'll hesitate to say useful, but you really can write practical programs with. So I'm not going to show you Pac-Man, I'm going to show you Hangman later on, which is close. Well, it's got three of the same letters in its name. So I will show you some sort of interactive programs and how we might get there. If you do want to try out some of these things I'm going to talk about, you could just go to idrislang.org/download. I don't know if there's a wireless network that you can all use here, but if you just go to that link and play with Idris instead of listening to me, that's perfectly fine. I will feel that I've done my job. I'm going to show you quite a few examples of programs as well as we go through. I'm not going to show you many slides. I'm just going to illustrate some of the ideas of type-driven development with lots of examples. So as I do that, please do shout out suggestions and shout out questions of what happens if you do something slightly different. So it's going to be in two parts. I will talk for I think about 40 minutes. Is that about right? Basically until Henry tells me to get off, and that should be enough time. I have about 2 hours worth of material. I'm not going to compress it to 40 minutes. So I'm just going to give you some of the basic ideas, and then something that I think is going to be really important is using precise type systems to explain why your programs are managing side effects correctly or managing resources correctly. So one of my favourite examples of this over the last couple of years, anyone remember the go-to fail bug? Yeah, some nodding. So this was essentially a C program where you have an if block, and nested in that if block is the command go to fail, followed by another command go to fail, nested the same but without any brackets around it. So obviously what always happens is you leap to the label fail. Now if your program is just something that you're hacking up for a bit of scripting and you're going to run it and it's not going to work, you can just try again. But if your resource bug, tracking the state of a security protocol, if your resource bug happens to be in a security system that's vital to the infrastructure of the internet, we have a bit more of a problem. So it would be nice if we could set up our languages, set up our programs so that if we made this kind of error, at least the machine would help us get through it, get out of it. So I'll show you a little bit about languages like Idris, and using scope type systems might help us get there. So, what are type systems for? Do we have any professional Java programmers in? Not many people want to admit to it. Okay. Scala? Yeah, okay, a few. What about, actually this is just for my own interest, Clojure? Okay, I thought there might be. So I'll tell you about half the hands have gone up. What else do people use? Any professional Haskell programmers in the room? I'm looking at Brian or... okay. If you program in a typed language, whether imperative or functional, you might be used to the type system or the type checker being something that tells you off when you make a mistake. So you write your program, you put it all together, you hope it works, you feed it to the, you hand it over to the oracle, the priest, who then sends it to the, then type checks it, and then typically it will come back and say, no, you've done it wrong. I think it's a shame that we use type systems that way in most programming languages. Types should be really there. I mean, one thing is that they're there to check that the program has the properties you intend the program to have, but I really like to see them as being to help you get to the right program. So rather than thinking of the types as being the type checker as being a thing that tells you off when you make a mistake, the type checker should be like your lab assistant or your personal assistant that tells you what we're doing next, or maybe fills in a bit of the program for you if it has enough information. I've started calling this type-driven development because we're putting types first. We're thinking of the type as being like the plan. We say to the machine, this is the type of the program, that is, this is the plan that we are going to execute together, we're going to work on together. And as we're developing a program, there's anything we do can sort of be broadly broken down into 3 steps. So the type step, that is, write down a type for a function or write down a type for some fragment of a program. The define step, which is where you maybe create a partial implementation of a program. So you'll define a program maybe by saying, okay, we're going to inspect that boolean now, or we're going to inspect that list now, and then the machine will tell us what we have to do in each steps. Or we might have the refine step. So the refine step is where we have a program, but we want to make the program a little bit more precise, or write a little bit more of the program. So there has to be 3 steps, so that you can say mantra, type, define, refine. I can't think of a word that rhymes with define or refine that means type, unfortunately. Not a good one anyway. But everything we do is going to be type, define, refine. We're going to go through this cycle for all of our programs. I'll just show you a few examples of that, so hopefully make those ideas a bit more concrete. Hopefully we're okay for font size here. I can't particularly easily make it bigger, otherwise it won't fit. But here I have, your simple Idris program that displays the string. So just to show the general workflow, we can load that into an Idris REPL. You can see that I've made the font so big that you can't see the banner very neatly. So we can check the types of things. So we can use this as a calculator. The colours are going to get bad in a bit. So I'll turn the syntax colouring off. This is a Scottish language or British language, so colour has a U in it. So we can do a few bits of calculations. We can check the types of things. So the type of main is IO. Can you see what's going on at the bottom, at the back? Should I lift this up a bit? I'll lift it up a bit anyway, because nobody said anything. So we can compile and run it. So :exec will compile and run it, and so on. So. What do I mean by type-driven development? Well, I mean types come first. I also mean that types are a first-class citizen of the language, a first-class construct. So being a first-class construct means that you can calculate types just the same as you can calculate anything else. So when we talk of functional programming, we often talk about first-class functions. So we can manipulate functions just like we can manipulate any other construct. For first-class types, we can manipulate types just like any construct. So I can write a function that takes a bool as an input and returns a type as an output. I'll just go through that quickly. This I'm using here is Atom. So Atom has a plug-in for editing Idris programs. So do Vim and Emacs, but I'm going to use Atom for this. And it really helps us go through this type, define, refine process. It sort of acts as our virtual lab assistant. So I've written the type here, and I'm going to say to Atom, right, I want to define that now. So if I hit the magic key combination, Control-Alt-A, it will add a definition for me. So what it gives me is a skeleton definition for that function. So the name, the parameter, and then that equals something. So functions, if you're not familiar with a Haskell or OCaml style notation, essentially what's going on here is we're defining functions by sequences of equations that allow us to rewrite the input. So this thing on the right with a question mark, this is a hole. So a hole is a part of a program that you haven't written yet. And the Atom mode allows us to look at the types of things. So if I, with the cursor over string or nat here, I'll hit Control-Alt-T, and it will give me down the bottom, it will tell me what the type of string or nat is. So this is a function type, it takes a bool, returns the type. I can also stick the cursor over this hole and ask for its type. So it says, in this case, it says, I have a variable called isStr, and I've got to return something called type. Now, you're probably completely familiar with holes, and you've probably been familiar with holes since before you went to school. It's something that you learn about in daily life. You know how to solve problems by filling in holes, and I'll actually show you. I'll prove this to you if you don't believe me. This is how I learned programming when I was about 3. I had one of these. This is a theorem proving device. I'll put it on here. So these things in here are the values, and I have some Idris laptop stickers as well. Actually, if anyone's interested. These things in here are the values. And these things around the top, these are the specifications. So this thing here, string or nat RHS, it's a hole just like the holes in here. So all I have to do, in order to fill in, to complete any of these specifications, is find the appropriate value for the hole. This is where I find, I was going to use the circle, but apparently I've lost the circle. So I'll solve the square specification. I'll implement square. So there we are, I've implemented square successfully. By the way, this also illustrates what type checking is all about. So if you program in a dynamically typed language, what's happening is, I'm trying to implement a program that does 1, and what I happen to have written is star. And in a dynamically typed language, what's going on is this. You're trying to do this at runtime, and this is clearly a silly idea, unless you have a hammer to coerce it or something that might do it. But in a statically typed language, the machine is going to say, well, obviously star isn't going to fit through 1. That's crazy. So this is think about this when you're programming in a statically or a dynamically typed language. If you're programming in C, of course, you have a backdoor, so anything can get in. So there we go. I will leave the theorem proving device for anyone if anyone wants to learn theorem proving later. They can have a play with it. Anyway, so all I have to do is exactly that. Is fill in the hole for a string or nat here. So the way I'm going to do it is this function is going to return if that argument is true, it's going to return the string type. If it's false, it's going to return the nat type. So what I say to Atom is, I want to do this. I want to implement this function by case split on isStr. So what I do is I hit Control-Alt-C, C for case split, and it splits that boolean into the 2 possibilities for the boolean. So I'll just complete this one quickly. And in that case, it's going to be nat, and in that case, it's going to be strict. So when would you run a function that calculates a type? This is obviously it's not a it's not a thing that you would do at runtime typically. You don't work with types at runtime. You work with types at compile time. The types are there to tell you a bit about what the program is doing. So we can use this function, string or nat, in some context where we're expecting a type. So where would that be? That would be like the inputs or outputs to the functions. So this function, length or double, based on the input is true. If this flag is true, then this argument type is going to be string. And if that flag is false, then this argument type is going to be nat. So I can write functions that work on different types depending on what one input might be. So I'll do the same thing here. If I look at the type of the length or double hole here, it says, well, you have a flag istra, which is a boolean. You have another argument x, which has type string or nat istra. So it follows that if I know more about what istra is, I should know more about what the type of x is. So this is going to be a refined step. We're going to refine the type of x by whatever knowledge we can find out about istra. So I'll do a case split on istra. And so now we know in this first case, length of double RHS1, we know that it's false. So it's going to go off, the type checker is going to go off and run this function string or nat, and we'll see that we're expecting x to be a nat. And in the second case, we're going to look at this, and we're going to expect it to be a string. So this might all seem a little bit abstract at this stage, and a bit, why would I want to do that? But you can pretty much guarantee that you've already a function that does exactly this, certainly if you've ever programmed in C. So printf. If you've ever used printf, printf has a format string. That format string tells the C compiler what the rest of the arguments are meant to be. And actually, the type of it in C isn't checked, and it tends to be hard-coded in C compilers to make sure that you've done the right thing. But if you have this kind of facility in the type system, you can just write printf. So you write there's a little bit of machinery to do to read the format strings. But essentially what you get is a function that takes a string, and from that string you can calculate the type of the rest of the function. So just to make that a bit more concrete, I'll actually do something with this program. I should have turned the colour off because these green bits don't help you on this. That is almost legible. So if I check the type of printf, it will say, well, printf takes a string and then we'll calculate the rest of the type. But if I give it some kind of format string, then it can compute what the type of that the rest of it is. And there's an SMD. There we go. So I could evaluate that with with two things of the appropriate type, and if I give it the wrong type, I should get a type error. So it says, I was expecting that to be a string, an int gave me a string. So it's kind of a small example, but it shows the sort of things that we can do, building things like printf that you might otherwise have hard-coded into the language, but you can build it directly in the language by doing some computation with types. So let's go with something a bit more exciting. Only a bit more exciting. First talk, so we don't get too exciting. I'm going to show you something that comes up an awful lot in practice in Idris programming, and that's working with lists with length. So quite often the kind of errors that I encounter when I'm programming in Haskell or Java, as I sometimes have to do, is I try to look up values at a position in an empty list, or I make assumptions that lengths of data structures correspond, and it turns out that in practice they don't. So a lot of the time when you're programming, you make assumptions about the form of your data, the inputs to your functions and the outputs of functions, and you write the programs assuming, with those assumptions in mind. And probably what you'll do if you're a good citizen is you'll write some tests. You might even write them before you write the program to ensure that those assumptions are things that you stick to. The thing with tests is that tests can only show that your program is broken, and we don't like knowing that our programs are broken because we have to fix them. If you write types carefully, then you can be certain that some properties of your programs really do hold. Not only that, because we have this interactive type-directed, type-define, refine style editing interface, we can use the type system to write bits of the program for us. So I won't say too much about how lists work. I'll just show you the type signature of append. So append is a function that takes a vector with n things in it. So this vect is a data type that we just defined. It's not built in, it's something you define yourself. There is a library for it. And the n here is its length, and then this a is the element type. And then here, the second input, its length is m, and the element type is a. And so if you're appending these two things, we would hope that the length of the result is going to be n plus m. So let's just go through the process type, define, get to the definition. So step one is to make a definition. So we make a candidate skeleton definition, and the machine will give us this initial clause. So this hint here, this %name, just says while you're doing interactive editing, these are the names you should prefer. So Haskell programmers, and therefore by extension Idris programmers, have this annoying habit of always calling lists X's and Y's. These are fairly generic lists, so they could contain anything. So if you see an S, that tends to be plural. So what do we have to do? Let's always look at the type of the hole that's come up. So what we have to do is somehow fill in this append hole. We need something of type a vector of length plus nm. So this plus is just it's a specific version of the plus operator that works on this kind of number. And if I do some kind of case split, if I do some case analysis on one of these inputs, I should get some more cases that I have to define, and I should get some refined types that I have to produce in each case. So let's do a case split on X's. So just to say what this notation is, these empty brackets, this means an empty list. This X : X's, I read that as X comms X's. That means the list with X at the head, and then the rest of the list is X's. So it's a list with at least one thing in it, and this is a list with 0 things in it, or vector with 0 things in it. So if I look at the types now, if I look at the type of append RHS1, I should see that I'm looking for so wide is a vector of length m. I'm looking for a vector of length m. So it knows that this thing didn't have anything in it. So it knows that the length of the result we're looking for is 0 plus m, which is m. We only have one of them available, which is y's. So what I'll do is I'll just hit the command control alt S. So that's S for search. It's S for the machine. You search for an answer. You search for something that might fill in this hole. So this is where we've got the machine being our lab assistant. We just look at the program and think, yeah, well that's obvious. So you figure it out. So it did. The only thing that works here is y's. And in this second case, what do we have? Well, we've got a vector of k things. We've got a vector of m things. We need to make a vector of k plus m things. This S means 1 plus. So we need to make a vector of 1 plus k plus m things. And, well, actually that's obvious too to the machine. So we'll ask it to search for an answer, and it says, well, that's probably what you're looking for. So because we had some precise type about what the length of the result must be, we only had one thing of type A available. We had a vector of k things and a vector of m things, and we needed one thing plus the vector of k and m things. That meant the machine could fill that in for us. So by getting a little bit more information up front, the machine's been able to help us out. Yeah, question.
So what we hadn't cased? What if we hadn't cased on the first argument and asked it to search for a result? What would it do?
It would fail at the moment, but it's completely believable that it could figure it out. There is another language similar to Idris called Agda. There are some different philosophies in how they approach what the purpose is. So Agda is more about sort of formalizing mathematics and theorem proving, whereas Idris is more about programming. Agda has a tool called AGSI that I'm jealous of, that knows how to do exactly that, where you could write down the type and it would generate you a few candidate definitions that are well typed. Now think to remember when you do that. I do tend to steal that sometimes. The thing you have to remember when you do that, even on these small examples, is that this is not a substitute for knowing what you're doing. It could present you something that isn't right. So you have to at least look at the result and see if you agree with it. And you might even test it. But it's giving you, if you have some, this is something often happens with certainly the kind of programming I do, you have to do a little bit of plumbing. You pull an argument from one place, send it to another place. It's just kind of boring to figure out the right way to do that. And machines are very good at that kind of plumbing, figuring that out for you. So yeah, by giving this type up front, we've got a little bit more type system has a little bit more to work with. Now, how am I doing time? Not well, so I'm not going to do. I'm going to show you the type of this thing. I'm not going to show you the implementation. So this is here's if you teach at a university, as I do, sometimes I want your students to do. I teach a second year course on data structures using Java, and I teach them how to work with linked lists. And sometimes I never quite feel evil enough. Sometimes I nearly feel evil enough to get them to write function that takes a linked list of linked lists and then transposes them. And I allow them to work under the assumption that the dimensions are consistent. And I don't know about you, but one reason I've never said that is I have no desire to implement it myself, because it sounds like a fairly challenging problem. Because you have to make sure that the lengths are right for one thing. You have to make sure that all the things link up together as they should do. And what we can do in Idris, in fact I am going to show you this. It won't take long. What we could do is just precisely state what the dimensions of a vector transition would be. So we have a two-dimensional vector here, so an n by n vector of this element type, and we want to come out with an n by n vector of this element type. So let's see what happens if we try to do this interactively, looking at types as we go. So first we'll ask the machine for a candidate definition. The only realistic thing I could do here is see what to do with the empty vector and then see what to do with the non-empty vector. With the empty vector, I need to produce a vector of, I need to produce m copies of the empty vector. And I can't be bothered to do that now. So what I'm going to do is I'm going to rename this whole rule and just make a candidate definition, a candidate function does that. So I say, right, there's bound to be a function that does this, stick it in the program and figure it out later. In the second case, well, it seems likely, when you're writing a function on a recursive data type, and you have, so x's is the inner list, it's very often a good start to just say, well, let's make a recursive call and the rest and we'll figure out what happens next. So we'll make a recursive call on x's, and then I'm still not sure what to do. So what I'm going to do is write a helper function, and I'm not even sure what type of this is going to be, so I'll ask the machine. Okay, so here's the type of a helper function, and this is one reason why I wanted a slightly bigger screen. There we are. I happen to know I'm not going to need x's. So I'm going to write this helper function that takes. This is if you imagine we've got a list of vectors of some length. So now we have the first one, and then we have a transposed version of the rest of them. So we have a vector of length m. So imagine m, and then we have several vectors of length m. So m vectors that have been transposed along here. That's essentially what this type is saying. So how do we write this? Well, let's look at the types of things. We have x has m things in it. X trans has m things in it. So I'm going to do a case split on x and x's. So I'm now sort of trying to glue corresponding elements of each of the first vector onto each of the other vectors. We know that the lengths correspond because we said in the type the lengths of x prime and x correspond. We've got m things here and m things here. So if I do a case split on x's trans, I'm only going to get the empty vector because that's all it can be. Because the lengths have to correspond. And so we'll just say to the machine, what's the answer going to be? Machine says it's going to be that. Good. And I'm not even going to think for the rest. I'm just going to do case split search. And there we are. We've written. We haven't done the empty cases yet. I'll because we're slightly short on time, I won't explain what's going on here. I'll just do it. But basically, all I'm doing is case split and search, and the machine's actually figured it all out. I can't actually remember how to transpose on vectors. So it's a good job that the machine did this for me. Now what I can do, I haven't written a main program that does this job, and what I do is just to prove that it really is doing transposing vectors. And it must be because if you've got an n by m vector and you use an n by n vector, there's not really anything that's going to type check other than the program that poses vectors. I suppose you could imagine slightly weird program, but the natural one is just going to be the program that poses the vector. So let's what's called that? It was called just to let's be controversial and pilot test it. Yeah, I don't care. We're not going to evaluate that whole. So if I say give me a 4x5 vector, it will then. So this is a test one generated, and then this is the transposed version. So we've compiled and run this, and well, we knew it was going to be a transposed version of the vector because it's type check. You know, type checks. You might as well ship it. It's just like diversion. Idris has a plug-in back-end system, so I don't see any reason why we shouldn't generate a version of this program on I don't know PHP. Because people might tell you have to write, you have to deploy a PHP script. That shouldn't mean that you have to write a PHP. So we could compile this program to PHP. So you get this warning if the program is incomplete and it says warning it might crash. But it's a PHP program. Still the same thing. So it's anyone fancy writing a linked list transposition program in PHP? Well, if you need it, it looks a bit like this. So this is what's coming there. That's actually when I write PHP by hand, it looks a bit like this. Anyway, so that was just a pointless diversion. So this is like the sort of functional kinds of programs you might write. But we're really interested in dealing with resources, side effects, and how might we be able to use this to write say security protocol or network communication protocols. So all of the ideas I've just shown you, once you're used to this functional programming, thinking about writing the type precisely, they all apply reasonably directly. Modulo learning a couple of other features. So I'll show you a small example I like to use for what's going on here. And that's just implementing state machines and showing the state machines you're working with. You're really working with them as you show. So this is my favorite simple state machine. It's a state machine representing a door. And I suppose if we're going to make this a computing related, we could imagine it to a robotic arm sliding or an electronic sliding thing or something. And the door can be either in the state open or closed. If it's in the closed state, there are two things we can do. We can knock on it, or we can open it. If we open it, we end up in the open state. If we're in the open state, the only thing we can do is close it. So we can't knock on an open door. I've decided. Maybe it's slid out of the way or something. You might recognise this state machine as like files. So if you can open a file. When it's open, you can read it and you can close it. So it's a similar sort of idea to open a file. Now how we might represent this in Idris. So there is a library dealing with effectful programs. Called effects. And I won't go into the details of how it works. I'll just show you how you express this kind of state machine. So we can describe doors, this door system as an effect transition system, where the thing to focus on here is on the right. So we can open the door if it's in the closed state, and that will go in the open state. Or we can close the door to the open state if that gives us the closed state. We can knock on the door in the closed state, and that doesn't change the state. So essentially what you see here, at least in this section, is a state transition system. And then down the bottom here, we can see a program. This type here says it's an effectful program, and the start and end state of the door is always closed. So we've got three actions. We can knock on it, open it, and then close it. And let's just see type checks. Good. Type checked. You can't see that on the screen, so I'll just load it into I'll load it into an Idris buffer so that you believe me. Okay, so that type check, because there's no error messages. What I could try to do is let's try opening the door twice. So we're opening an open door. So if we go to fail again, if we go to fail twice, what happens? Well, it's not quite like that because there's no program. But let's try reloading that, and it says. So you need a little bit of decoding here. But it says I'm trying to when you run an effectful operation, it tries to find some evidence that effectful operation is something that you're allowed to do. And it can't find any evidence. It can only find an open door, and it's looking for a closed door. So I mean, I suppose you could read this error message as it went wrong and line number, which is what I usually do. So let's put that back. Now this is a way of representing state transition systems. But the thing is, in the real world, state transition systems aren't quite cooperative as that. So like opening a file isn't always going to work. The outside world has some impact on what your program is doing. If you receive a message from a network, you don't necessarily know that message is going to be the one going to your protocol. You don't even necessarily know that you're going to get the message. So as well as saying what states you want to happen, we have to let the machine tell us a bit about what's happening to the state of the world. So we can take this a little bit further, and we can say that opening a door will return us a result. Either it's jammed or it's not. So opening a door might fail if it's either locked or in this case it's jammed. So it's a WD-40. So this returns a result of jam. And the state we go into, so we start it'll only work if we're in the closed state. But the state we go into is computed from the result of this operation. So you think right back to the beginning, where I was saying, you get a string or an int depending on whether this Boolean is set. Well, this is exactly the same. This is where this sort of becomes useful. So we're getting either a closed door if the door is jammed, or an open door if the door is not jammed. Now what this type means in practice is that when we come to writing the door protocol, I'm trying to knock, open the door, close the door. I've not actually checked whether opening the door succeeded. So if I try to compile that, it says it went wrong. That's a pretty reasonable way of interpreting that. Because I didn't check whether the opening the door was successful. So essentially, all I can do is bother to check. By the way, I can. The great thing about holes. Remember the holes? We need to fill in some holes. The great thing about holes is if you're not quite sure what to do next, you can always stick a hole in your program and say to the machine, help, what do we do next? If I say help, it says. It says you've got a case block, and it says what line number the clock is on. So that's actually more helpful. You look at that and you think, there's lots of stuff. That can't possibly be helpful. But it said that there's this case block, which means we have to inspect. In fact, it says what we're applying it to. So we basically have to inspect this variable. Okay. So I'll do that. I don't like typing case, so I added a shortcut. Do it for me. So if we check the result of this, so again we can do a case split on this like we've been doing. So we now got two cases where the door is jammed or not jammed. If I inspect the type now, it says in this jammed case, you've got a closed door, and you're trying to get a closed door. This .io here means I'm allowed to do some console.io. So let's do some console.io. Let's make the sound of someone who can't open the door. And I suppose we could have another go. We could go back to the beginning. And then in this case, I could quit. I could just so anyone see what's going to happen here? Will this work? No. Why won't it work? I haven't closed the door. So if I reload it, it says, "Were you born in a field?" So I fix that. So atom is very helpful sometimes. It's corrected my grammar. I really did want the low C there. I don't really use atom. I'll out myself as a Vim user. So that type. So it means that not only have we followed the protocol properly, we've checked all of the possible error conditions before we carried on. By the way, there's no reason why we have to do this test immediately. So just because I've done the test doesn't mean that we have to do it later on. So at some point, when we want to make any more progress with this door program, before we close the door, before we return, we're going to have to see whether the door is open or not. But I can do anything before then, as long as before we do anything with the door, we actually do Bob's check. Right. One final thing. Because according to my timer, I have about a minute. I don't know if that comes with Henry's time, but he hasn't dragged me off yet. So extending this idea, I thought it would be a bit of fun to see if I could encode the rules to Hangman. And then write a verified version of Hangman, because that's what the world's crying out for. So just to give you a very sketchy idea of what's going on here. This Hangman thing is just like the door thing we've seen. So the door thing was parameterized by whether the door was open or not. Well, this is parameterized by the state of the Hangman game, where I have a number of guesses left and a number of letters still to guess. So this remember that S means plus. So this means I have one plus G guesses left, so that's at least one guess available, and I have at least one thing still to guess. And so guess is me saying to the state machine, I am going to guess this letter, I'm going to guess a particular letter. And the machine will say back to me, either you got the letter right, or you got the letter wrong. If you got the letter right, so true is you got the letter right, you'll see that I have the same number of guesses, some wrong guesses available, but I have one fewer letter to guess. I don't know why I used double letter. I did. Because I'm a functional programmer, and therefore I have to use letters where words would do. And if I get it wrong, if it's the wrong guess, then I've got one fewer guess and the same number of letters to guess. So we'll eventually glue all that together into an implementation of the game. I'm not going to go through all the details here. So an implementation of the game, so we'll enter the guess, we'll pass the guess on, so we'll process the guess, so it's just taking the first character from the guess. When it processes the guess, it's going to processing the guess starts in the stage where the game is running, and it will end in the stage where the game is not running, meaning that it's just going to loop around until the game is over. So basically, I can't half-write this. I can't write a version of the game that just quits in the middle. It's got to complete the rules of the game. And so if the number of letters gets down to 0 of 1, if the number of guesses available gets down to 0, I've lost. So assuming when you have to look a bit longer than I've given you, you look at the state transitions that I've given rules, and you believe that they read the rules of Hangman, then this implementation of the game can't cheat. I claim. And just to show that does run. By the way, I haven't implemented enough of the operation PHP back for this to compile. Otherwise, I would have done this as a PHP game. Life's too short. I only wrote the PHP back end for a bet. So there's JavaScript. There's Python. So they're plugins. They're not maintained by me. They're not part of the domain distribution. So there's an API that essentially gives you the intermediate syntax tree. So if you have a platform that somebody tells you you have to run on, then you could find a way. And the PHP backend is about 150 lines of Haskell, just to give you an idea of the scale of what it takes to write a backend. It's not an awful lot. Right, the words here are programming languages. So. Rips. A isn't in it. E is in it. What could this be? I don't know what this is. Any ideas? There we are. There we go. So just some amusement. This really happened when I was writing this. I got this wrong. I looked at the wrong variable. I checked whether I'd won the game, and so the number of variables for winning the game was down to zero. Oops. Let's compile it first. And it said no. And it said no in a very confusing way. Well, I don't know. If you know what you're looking for, you see that you've got a running G1 and you're actually getting zero G. So it's sort of the wrong number has gone down to zero. So that really happened. There's another error that came up that really happened, which is the set of words I gave it. When reading that set of words, I never gave any guarantee that the words had a letter in them. So the strings. String could have zero characters in it. Now, what would have happened if it had read the file and there were zero characters in the word, and I hadn't thought of it, was it would either have crashed or nothing would have happened. A very boring game. But what actually happened was I got a type error because and that's the reason for this case here. Actually, you've got to actually check whether there's zero letters in it. So the fact that I had this just one thing in type in this abstraction of the hangman game meant that I got a little bit of a hint that I'd done something wrong. So there you go. Right. I better stop there because
minus 2 minutes.
I've got minus 2 minutes. But there is one more thing. Which is a bit of shameless self-promotion. If you're interested in reading more about this, there's a book in development about 10 chapters in. I have a special secret code for getting 39% off if anyone is interested. It's 39 Brady. It's not hard to remember. Okay, so I'll stop there. Thank you for your attention.
We probably could do probably two questions. Got any for Edwin?
Yeah, so you mentioned that the language is backward complete.
It's backward complete. I actually heard far from complete, which is also true.
So is it total?
It's right. There's a whole can of worms. We got all night. So it is total. You can relax that, so it will check. But I sense where your heading is total and incomplete don't live together.
I'm not sure.
Well,
I think they
perfectly fine. You can just because the programming language is total doesn't stop it being pure and complete. What happens is you separate the terminating from the productive. So you have a thing that runs forever. You know that every step it takes is going to produce some more another world state or more going on. That's a whole kind of work. I find it fascinating.
So has he got code data or anything like that?
So you've got productive structures and you've got basically either consuming data or producing data. If you put the two together, you have pure incompleteness as well as
you have that in Android. You have code data in it.
That's actually what is occupying my mind most at the minute. The thing that I would have loved to talk about, but completely inappropriate for this meeting. So you want to talk about it after that?
One more is quick. Okay, so say thank you again to Edwin.
Thank you.
We'll take a quick 10-minute break, and then up next I think we have Bob. start to make your way back to your seats. We'll kick off in a couple of minutes. Okay, well, on stage, Becky, who's going to talk about multi-paradigm programming. Are we there yet?
We made a proposal. We made a proposal. have function, and it's got body P, we've got RQ, and what we do is plug into where X is P. And then we take one of these fans and just now, and it just doesn't work. We've got this function here. This is ML lambda, so then we've got the top. And it's that X by P. Then we can't just P, can't easily just be some substitution. We made function program as well. I try to get problem here. I kind of think that this language is meant to be more paradigm, but they're really more paradigm in your mind. So you can be very good. You don't do anything here. Then you can so this is fast and use more where it's kind of what they're saying in classical, you can pretend you're using a nice pure language, but as long as you're fast, kind of pretend whereas what you want is multi-paradigm as well. Let's try to function. The idea to make it fast language. Before the second part, just put things together using semicolon under sign, but there's no way you can go back from there's no way of saying things that does something. So this is paper 1991 by John Reynolds. There we go. Well, yes, the whole paper is S. Nice one by one the essence of L. Yes, of L. There's the problem solved, and that's now fails. Yes, and I'll go on a bit sarcastic. But the idea is rather than having a command thing, I mean, you go to Java and you say, well, what's the whole thing? So rather than being commands being and the idea is we have type commands, and we put them together using these algebra. We have skip commands, variable, command assignment, read variable, and nice now is we now get this property, changing this is going to be give me back command does one. And we can just substitute because semi-colon command not imagining the thing to make something happen. We can also take comparative program. So the idea is probably here. There's probably function 4 where we have two arrays and A overlap and big. So again, John Reynolds has probably the idea although it's tactile now a bit fit. It's long been known where I normally rise with underlying procedure mechanism. Here's powerful just means you can create copies of overlapping variables. And it comes up with three principles. If we have two identifiers, so variable names and program, all the identifiers separate programs to mean these two programs we run so if all the variables are set there, the program in terms of their and if they've got different names, then they point different nice rule. And sometimes you can have passes read only, and they are allowed to fit. And then next round define it. This is a the reason why you want to Vegas is you can get nice parallel. So paraphrase can do first for an operating systems in the early 70s and worked a lot in parallel programming, and then he was really disappointed in Java. And so much so we wrote this paper. So when he says security, he doesn't mean money savings. In the sense that you can write from the job via their own they come up with problems in the past, mistakes in Java, which they cannot use the language itself. The meaning, there's no way you can observe the Java, which is not painful, very easy like that. So he says, Java's most serious decisions use French language to run those features. This is basically the state of the art, right? You come up with a French language, and you say, well, we're just going to run two things at the same time. Really very subtle, fast, and then we play the program wrong. There was lines, especially very common. The fact it has the very first version synchronized as keyword. It's built into the entire monitor. If you read this paper, it contains a lot about the way they've done this. I would say that they designed it to be four parameters from the very start. Possibly what they intended to read or but they were hooking it safe parallelism and they failed. So that's a control concept the type of the last bit of function is arguments not clear with themselves. That means every time function must be fresh in terms of pairs without clear. So what does this mean? This means French conversation. The second one we did because otherwise it wouldn't be enough together. But we can also have parallel things. And this means this command don't do each other. We get no database. A nice safe language for writing things. And so the point is that I think by changing the way you design privileges to put the various types, we can get multiple paradigm in the world. You don't have this thing where you have a control there's other stuff where you learn about how to use it. The programming language helps you use it. And simple reasoning functions commands means that we get safe parallelism and faster code using our code. And going back to Rich Hanson's conclusion of his research career, the programmers no longer see the need for empirical than I currently with creative years in rigorous concepts compromise about programming. And I'd like to really fix this. I think we can do a lot better. Thank you.
Any questions? Start work way back.
So are there any languages that go part way towards?
Same question here as well. Yeah. Any different questions?
Yes, I'm working on the application of
I think we're done. So thank you much again. Straight on to Michael. Just on to Michael.
Check. Can everybody in the back hear me? Okay. Oh, there it is. All right. The title of this talk that I submitted was something like "What the hell are monoids?" But I decided to rename the talk at the last minute, say about 20 minutes ago, to emphasize what I think is the bigger point of the talk, which is that simple math leads to powerful programming. And the rest of the talk is really just an attempt to prove this using an example, or if I have time, two examples. So probably just one example. And that example happens to be monoids. And if you don't know what monoids are, Great, because I'm going to tell you what monoids are from the ground up, no assumption of background, using examples, and then tell you why I think you should care and why they lead to programming. So, what the hell is a monoid anyway? It's a binary operator that's associative and has an identity element, and I'm going to tell you what each of those three things means. So what's a binary operator? Well, it's a function that takes two things and gives you a thing. Pretty simple. And here's a list of examples. So adding two numbers. Takes two numbers, gives you a number. Taking the union of two sets, right? Giving you the set that contains all and exactly the things that are in either of two sets. Concatenating two strings. Taking the maximum of two integers, or dividing two numbers. These are all binary operators, so they are all candidates for the position of monoid. Now let's see how many of them pass the interview. And throughout this talk, I'm going to use the dot symbol to represent some arbitrary monoid. I don't care which. And so A dot B means two things combined using the binary operator that we're thinking of. So it has to be a binary operator has to be associative. What do I mean by that? I don't care where you put the parentheses. So this equation characterizes that. It says if you're combining three things, it doesn't matter whether you first combine the things on the left and then combine them on the right, or whether first you combine the things on the right and combine the thing on the left. So how many of our candidates pass this test? Well, all of them except division, right? Adding two integers. I don't have to tell you what the parentheses are. 2 plus 3 plus 4. I didn't pronounce any parentheses. Set union. String concatenation. Maximum of two numbers. Three numbers. Same thing. Division. It does matter, right? So in general, A over B over C. I have to tell you which one I'm taking the division of first. So a specific example would be what? 1 over 2. Right? If I say 1 over 2, that's just 1 half. If I say 1 over 1 over 2, that's 1 over a half, which is 2. A half isn't 2. So division, I'm sorry, you do not pass. You are not a monoid. Okay. The other thing you need, the only other thing, is the last thing. You need an identity element. has to be some value, which I've written here as ID for identity element, that when I combine it with something else, with your monoid operator, it does nothing. It does nothing. You just get back the other value. Right? So for integers, for addition, that's zero. Adding zero does nothing. It's the boring element, if you will. Right? For union, that's the empty set. Unioning with the empty set does nothing. Boring. For string concatenation, it's the empty string. For integer maximum, well, actually there is no element. Taking the max of that number, some other number will always give you the other number. At least when my number is integer, right? If I say take the maximum of x and 0, well, if x is negative 4, that gives me 0, not negative 4. So there's no least integer is the problem here. So integer maximum is not a monoid. And that's actually it. That's all monoids are. Associative binary operators with identity. Really simple math. And one of monoids are so simple that they show up everywhere. And to show this, I'm going to give you a whole list of examples of monoids. So matrix multiplication. Matrix multiplication is used a lot in computer graphics. It's used in machine learning. You have two matrices with appropriate dimensions. You put them together. And this is a monoid. Doesn't matter where you put the parentheses. And the identity matrix serves as your identity element. Multiplying by the identity matrix does nothing. If you have sorted lists and you merge them, this is also an associative operator with an identity. It's associative, right? So the merge step in merge sort is where this comes up. The identity is the empty list. The empty list is always sorted and merging with the empty list does nothing. Unix commands actually form a monoid, right? To combine them, you put a pipe symbol between them, right? And you don't have to say where the parentheses go. And there's an identity Unix process. Cat. It just takes the output of the process on the left, types it. I suppose the left is over there for you. Takes the output of the process on the left, types the process on the right. So if I have any pipeline, I can insert anywhere in it, and the same thing will happen. Mostly. I'm ignoring some things about standard error. Yeah, I don't know. Maybe someone who knows Unix better can tell me whether that's really the case. Really, in no circumstance will inserting cat change anything other than timing. Does anybody have? Okay. Yeah. If you have function. There you go. It'll use up one more process ID. So if you're trying to guess the process ID of things based on where they occur in your pipeline, which is a bad idea, then your code would no longer work. Yeah. Yes. And you'll notice monoids don't need to be commutative. So associativity and commutativity are different things. So it has to not matter where I put the parentheses, but the left to right order totally can matter. Right? And another example is string concatenation, which is a monoid. In some sense, the monoid. I'm not going to explain what sense it is. If you want to know that, you can ask me afterwards. But left to right order totally can matter. So matrix multiplication is not commutative, but it's still a monoid. Right. Composing functions, another example of a non-commutative monoid. If I have two functions that go from the same type to the same type. So say from the natural numbers, I can compose them and get another function. And again, I have f, g, and h. It doesn't matter where I put the parentheses. F composed with h makes sense. And the identity element is the identity function. It does nothing. But it's not commutative because adding 2 and then multiplying by 2 is different from multiplying by 2 and then adding 2. Some more interesting example. Regular expression under choice. So here, unfortunately, parentheses in a regular expression do something slightly different than what I mean by parentheses. Right. So you have to use non-captor parentheses to get this in most regular expression engines. To see that it really doesn't matter where you put the parentheses. But basically, right, A, B, or C makes sense, and it doesn't matter which order you think of it in. And more general than regular expressions, context-free grammars, which is just another formalism for talking about parsing strings. So those are some examples. If you don't understand all of them, that's fine. Hopefully this gives you a little more intuition for what monoids are or do. Are there any questions before I go any further? Okay, great. If there are ever any questions or anything is unclear, please feel free to ask me. What are monoids good for? I told you why you should care about this incredibly simple thing. Well, you should care for three reasons. Well, maybe you only care for 2 of them. First, they give you some functions for free. They're an interface that you can program against without knowing anything else about something, but that it is a monoid. You can write interesting and useful functions on it. The second common useful for parallelization, which I will explain later. And third is they're useful if you want to start exploring algebra and why it's useful. They're a good simple starting point. So if you're giving a presentation, you want to use monoids rather than a more complicated algebraic structure. So now, what I mean by functions for free. Well, this is a bunch of Haskell code. If you understand it, great. If you don't understand it, it's not that interesting. What it says is strings form a monoid under string concatenation. Right. And this is just how Haskell says that. It says the operator is string concatenation. This line says, and it says the identity element is the empty string. As soon as I've written without ever writing a definition for the function mconcat, which I had before never heard of. I just said this is how strings are a monoid. Suddenly mconcat became able to understand lists of strings. I got a function for free that I didn't have to write the implementation of. I just needed to say this is what string is as a monoid. And this is because mconcat is written against the monoid interface. It works with any monoid. And what it does is right. I told you it doesn't matter where you put the parentheses, right? So it uses this operator string append to join together a list of things. And because it doesn't matter where I put the parentheses, I don't need to care about in what order string append is applied. So right. What mconcat does is it actually does join a list of things together using your binary operator. Turns your binary operator into an array operator. Of course, for performance reasons, I might still want to know in what order. So there's always leaks in your abstractions, and one of the leaks here is performance. However, speaking of performance. mconcat can be parallelized. So how does that work? Right? The idea is, if I have some big long list of things, and I have a binary operator that I happen to know is associative and has an identity. I also have a lot of processors, right? And maybe this operator is expensive to compute, and I want to use many processors to compute it. What I do is I take my big long list, I split it in half. Let's say I only have 2 processors. I split it in half, send the left half to processor A, send the right half to processor B. Each of those computes mconcat. It takes all of the elements, joins them together using my monoid operator. If I have n processors, I might want to recurse here. Forget about that step for the moment. Once both of our processors return their value, I join them together using my monoid append operator. Right, using the monoid operator. And because it's associative, it doesn't matter how I split up the list, right? I don't have to worry about off by 1 errors, whether when it's an odd number of elements, I split it at n over 2 or n over 2 plus 1, it does not matter. I could split up the list into one element and a bunch of other elements, and the only thing that would go wrong is my code would be slower, right? And if you have many processors, you just split it up into, you know, as many little lists as you have processors. This trick is the essence of MapReduce. So MapReduce is a framework originally from Google for doing parallel computation on massive data sets. And it's fairly complicated because, well, it gives you a bunch of nice, useful things like sorting built in. But the key insight is if the function you're trying to compute is associative, if it doesn't matter where you put the parentheses, you can divide it up as you wish, send it to a bunch of processors, or to a bunch of different computers, compute the results separately, join them together, and not have to worry about which node did what. So mconcat, parallel mconcat, is the essence of MapReduce. So that's monoids, in essence. So there's this incredibly simple idea in math, right? It's a binary operator, it's associative, has an identity element. They show up everywhere. There are loads of different monoids. And yet, just by knowing that something satisfies these properties, you can do interesting things with it, like MapReduce. And so now I've taken 15 minutes of my 20 minutes, so I don't have time to go on to semi-lattices. So, are there questions? Yeah?
You said string concatenation was demonoid, and you said to wait until later to ask why.
Oh.
Is now a good time to ask?
Sure, as long as nobody else has short questions.
Sorry.
Okay. So the mathematician-y way of saying that it's the monoid is to say that it's the free monoid. Specifically, strings to a mathematician are just lists of characters. List is the free monoid, right? List is the monoid. Why is that? Well, if I have a binary operator, right, and I know nothing about it, then the only way to represent the binary operator applied to something, right, if I know nothing about it, I don't know how to compute it, I don't know that it's associative or commutative or anything, the only way to represent a computation which uses it is in this sort of tree format. You might call it a syntax tree even, right? So if I was trying to represent the computation A combined with B combined with C, I would have to remember the parentheses, right? So it would be sort of, hey, there's a whiteboard. I don't know whether this is a good idea. Maybe I won't do that. There is a marker. What if I know a little more about it? What if I know that it's associative? Then I don't need to remember where I put the parentheses. If I don't need to remember where I put the parentheses, what data structure can I use for representing an arbitrary expression whose sort of primitive values are, I don't know, numbers, that is combined using some operator that I don't know anything about other than that it's associative? A list, right? And that's not quite right, because I do need to know that it has an identity. Otherwise, what does the empty list represent? Right? It doesn't represent any particular value. There's no expression in terms of my binary operator that the empty list can represent. So I can use a non-empty list. Was that actually what you said?
No.
No. Okay. If I know it's associative, I can use a non-empty list. If I know it has an identity element, then I can just say the empty list represents that identity element. And there I've got it. I've got a representation of any expression that uses an operator that is associative and has an identity element, which is to say any monoid. And the data structure I use for that is a list. And if I have two expressions represented this way, and I want to represent combining them with the monoid element, what I do is I append them, right? And that's why it's the monoid, because it can represent any monoid. And then once you pick a particular monoid, you can take any list and turn it into the value that it represents. And that is, in fact, exactly what mconcat does. So that's what I mean when I say that strings, or generally lists, are the monoid. Does that make sense to everybody? Cool. Any more questions? Yeah.
Doesn't meet the interview standard for being a monoid because it doesn't have an identity, and I can see that's obviously true in a kind of pure math sense, but ultimately we're running it on a computer and there'll be some limit to what you can represent as an integer. So does that affect what can be, like, for practical purposes,
Sure, yeah.
a monoid?
If you know that you're going to be representing your integers as 32-bit integers, you can use the minimum possible value as your identity element, and it will work. As long as you don't mind getting the minimum possible integer when you ask for the, mconcat of an empty list, which might be surprising, but it works. All right, any more questions?
Well then, thank you very much. A quick 10-minute break and then have our final speaker.
Oh, yes. Oops.
And actual fishing pod. Thank you very much. Right. So which way that's on, that makes sense.
merging kinds of types.
Okay, folks, we can take seats again.
Very quiet.
I'd like to welcome our final speaker, Maurice, who we're very lucky to have. He stepped in at short notice to this talk, so thank you very much for that. We're very, very lucky, actually, because among many other things, this is a man who wrote a book I refer to still probably ever so often, it's like being over 10 years old, which was Java Generics book. And, well, he's done many, many things since, so we've been very lucky to get him. So I shall pass you over.
Right. Thank you very much. Can everybody hear me? Yeah? Can anybody not hear me? Put your hand up if you can't hear me. So, thank you very much to the organisers for inviting me, and apologies for not being Bodil Stocker, whom I'm sure would have been... but anyway, I'm not, so I'm here instead. I'm not exactly certain what I'm going to talk about tonight because I'm not exactly certain where people are. I'm having a lot of trouble these days in talking about Java because of the adoption is kind of intersecting with what I'd like to talk about. So I used to be able to talk about Java 8, fairly confident that it was going to be something new to everybody. But now Java 8 is getting adopted, and so I'm in a kind of difficult situation of sometimes having to explain pretty elementary things about it to half the audience, while the other half sit and drum their fingers, and then losing the first half while the other half get interested. So I know we already had, Edwin already asked you this question about how many people are programming in Java, but very few hands went up. Could I just check again how many people kind of feel comfortable, not necessarily programming every day with but feel reasonably comfortable with Java generally? Okay, so that's actually nearly everybody. And how many how many people feel reasonably comfortable with the functional features of Java 8, with the so-called functional features of Java 8? Okay, so that's actually not very many at all. So I'll treat this as something like an introduction to almost functional is actually a pretty good title here. So the ground has already been laid for by Robert's talk about how it would be really nice to combine functional and imperative paradigms within a single language. Only curiously enough, he didn't mention Java at all. I wonder why that was. And also we'll come on to see that Michael's talk was also very interesting. So so this talk used to be called, it probably is still kind of called Parallel Ready Java Code, and Henry pointed out that actually managing mutation in imperative language is what we do all the time. But we want to manage, in Java 8, what we want to do is actually have some functional-like features, and then mutation suddenly becomes a big problem because Java programs are in fact all about mutation. So let's see we're going to see how that works, what kind of functional features we can get in, and how we can manage the inescapable fact that Java programs always end up doing a lot of mutation. Right. So I'll skip the slides about me, more or less. I'm these things in the Java community, and I'm Edinburgh based, as a hint to people who are looking for someone who's Edinburgh based. And as Henry mentioned, I've written a couple of books about Java. The big releases seem to attract my attention. So Java 5 was a big release, and I collaborated with Phil Wadler on a book about generics and collections. And for Java 8, I wrote a book about lambdas and streams. It's only got lambdas in the title, but it turned out to be more about streams, and it's material for what I'm going to be talking about tonight mainly. So, if you're not very familiar with the Stream API, I think this is by far the most interesting part of Java 8, and it's going to influence the style of programming in Java much more than any change that there's been since the language began. So it's really quite interesting, and if most people here aren't familiar with it, I think probably quite a good idea is to talk about what the idea a good idea for me would be to talk about what were the design motivations which went into it. So the ideas in the Stream API are partly drawn from, well, they are actually mainly drawn from functional programming. So I ended the book by saying that for 30 years or more, I've been listening to functional programmers saying that they're going to take the world over, more or less. And gradually, I'm sort of seeing this sense of satisfaction creeping over them, because they believe that it's happening. And to some extent, that's true. A lot of the big ideas that came into Java with the latest release actually really did come from the world of functional programming. So the main ideas in the Stream API two of them actually that are really quite old in the context of imperative languages. The idea of pipes and filters, which will be familiar to anybody who's ever used Unix on the command line at all, and the necessity for parallelism, which we've known about for a really long time, but which is becoming more and more pressing because of the advent of multi-core hardware. And so within the necessity for the mechanisms for parallelism are going to involve the kind of recursive decomposition that Michael talked about in the last talk, and we're going to see that the recursive decomposition stream transforming operations that will actually work on the map reduce paradigm essentially, and then parallel merging at the end are the themes that we're really going to have to take up. So let me talk first of all about so overall my motivation in this talk is to try to give you some of the what lay behind the design of Java 8, and that's very pretentious of me to try and do that in 40 minutes or so, but I'll give it a go. So one idea is the idea about pipes and filters. If you use Unix on the command line, then you'll have seen this kind of thing plenty of times. Here what we're doing is we're getting the process table, and we're filtering each line from the process table over a particular text string. Then we're selecting certain columns from it, and then we're taking the first five or 10 lines of the resulting output. And this idea, and you get this repeated in other places as well. The first place this idea of pipes and filters came up was in fact in Unix, but it's turned out to be a very useful idiom in other places as well. So you get the same kind of thing in enterprise integration patterns and elsewhere too. The advantage of this pattern there are many of them. One is, from our point of view, you don't need to worry about intermediate variables. A program written in this style is going to be very clear because you don't have to worry about names and polluting your namespace. And also, in Java terms, you don't have to worry about intermediate storage either. Intermediate storage is quite expensive in Java, typically because you incur big costs of garbage collection. You can. And it's often very important to be able to use lazy evaluation in this style. So if, for example, you're looking for an element that's going to satisfy some predicate at the end of the pipeline, you won't need to evaluate every single. In this case, you won't need to evaluate every single element of the pipeline before, provided you can actually find something an element. The element that you're looking for, and we'll see how this works as well with Java streams. And probably the most important of the advantages are that it gives you this opportunity to build large tools out of small components very, very easily. It's a very flexible tool building. Sometimes called the Unix philosophy. Philosophy is a big word for an operating system, but actually it's like a culture. Say small tools that you can easily assemble into big things. Doug McElroy, who invented the idea of the Unix, had three maxims for this. He said, write programs that do one thing well. So all of those Unix commands that you saw on the previous slide are really fairly limited. They don't do very much, but they can be combined very easily. He said, but what's important is that they can work together. And he also said that you should write programs to handle text streams, because everything understands text streams. So I used to say, well, 2 out of 3 wasn't bad, because this is not going to be the case for streams in Java at all. But actually, we have something of the equivalent of that. Somebody pointed this out to me when I'd already given this talk quite a few times and then had to score that bottom line out. And somebody pointed out, well, actually, there is some kind of common denominator of the things that we'll pass down Java streams. That is value objects. So value objects, and of course primitives, because we have streams of primitives. So really we are in fact fulfilling the general idea. With Java streams, we are going to fulfill the general idea of pipes and filters. Okay, so for the examples I'm going to use in this for this talk, the value objects I'm going to be passing down the pipeline is something pretty straightforward. I'm just going to have a person class. With three properties, an enumeration type, which I won't define, a string and an int, just for the sake of demonstration, and we'll have some person objects, and we'll assume that we've got available to us a list of person objects, which has got some sample instances in it. Now, the kind of useful things that we can do, the sort of style of programming that we're going to be doing from Java 8 onwards. If we want, for example, to find out whether all of the instances in this list of person represents an adult, we could, in the past what we would have done is we would have iterated over the list, and we would have had a boolean which we would have repeatedly changed according to the age of the instance that we're looking at. Now we'll write something rather different. We're going to take this list, we're going to feed it into a stream, and I'll go on to talk about what a stream is in a moment. Then we're going to pass it through an intermediate operation. Each person will be transformed. Each person instance will be transformed to an int using this function here. That's a method reference, which is a kind of lambda. Basically, what it's saying is we're going to apply the getAge method of person to the instance that is being passed through, and that will transform this stream here of this stream of person objects into a stream of ints, and then we'll feed that stream of ints to this terminal operation, or match, which will return a boolean result depending on whether this predicate here, another function in effect, is satisfied for all of them. So the predicate here takes each int and evaluates whether it's greater than or equal to 21. So if you're not used to this style, then you're looking at this and thinking, well, this looks like it's going to be very complicated and difficult compared to iteration. I'm not going to spend time in this talk motivating why, after a while, you come to see this as a much better style. So I'm afraid I'm just going to take that for granted here. Here's another example. We're going to print the names of the inhabited cities, and again you can easily see how you would do this with iteration. But we have a different style here. We're going to take the list of people. We're going to stream them. We're going to feed them into a stream. We're going to map each person to the city that they live in, and that they values for provide, but can also be generated by a generator function, for example. So not necessarily associated with any storage mechanism. Can be the sources for streams can be collections, arrays, generator functions, IO channels, all this kind of thing. Streams, something completely different from anything to do with iterators is streams can be in their essence parallel. So I'll come on to talk about that quite a lot, because that was a really important motivation for why the Stream API ended up the way that it did. And they can be infinite. So if you have a generator function that goes on indefinitely generating a stream, then that stream will be infinite, and then lazy evaluation is going to come in to be very important, because of course you can't strictly evaluate an infinite stream. That would take you forever to do that. So what's going to be important is that you should be able to find some terminating condition in order to get a result in finite time. Most of the streams I'll be talking about here, but not all of them, will be reference streams. That's streams of reference objects. There are also primitive specializations as well, both for efficiency and also because some specialized operations, like for example terminal operations, which will calculate the arithmetic totals, and that kind of thing, are it's useful to have streams that consist of these primitive types as well. So we've got int stream, long stream, and double stream. So to give a quick survey of the stream API, this is kind of background as to what it looks like. The sources for sequential streams. Stream sources supply elements one at a time. Why did I say that? Well, I must have said this because I was thinking about sequential streams. So, in general, actually, the stream sources are splitterators, which we'll come on to talk about in more detail later on. So the idea of a splitterator is the cute name for something that can both iterate over say, a collection, though, as I say, collections aren't the only sources. But let's think about collections for a moment. Splitterators can iterate over a collection, but they can also split a collection down for parallel processing. So the general idea of a splitterator is that under the right conditions, given, say, for example, an array list, it will split the array list into two, then again into two, and so on, in very much the way that Michael described, in order to support parallel processing on multi-core hardware. But in other circumstances, given a different kind of stream source, say something that can't be split, because many stream sources can't be effectively split, then it will iterate over them as well. So it has these two different ways of proceeding. There are lots of methods in the platform classes for generating streams, and though the most important ones in practice will certainly be the stream methods on iterable, and therefore on collection, as in this case. That's the source of streams. The stream life cycle is that it begins with a splitterator. It goes through one or more, or actually zero or more, I guess, of these intermediate operations here, which are probably, I think, once you get that, once you see them in action at all, you will kind of get the idea. Filter is an intermediate operation which selectively drops out elements from a stream. Map, you've already will transform each element to something different. Flat map, I'll talk about in a moment, for debugging. Peak will allow you to watch the elements as they go by. You can sort a stream. You can deduplicate it. You can truncate it at the beginning or at the end. Sorry, at the beginning or at the end. So here's a kind of insultingly obvious animation for how filter works, and I hope that maybe as time goes by and I do some more animations, you'll see why I started off with this. Supposing we have a stream of string here, and we want to pass it through a filter operation, this intermediate operation, which is going to drop out all of those elements which don't satisfy that predicate. Here, the predicate is that the length must be less than 4. The string Jim passes that, and so therefore it passes on down the stream to the next intermediate operation. And here comes Bill, and Bill doesn't satisfy that, so Bill doesn't pass down, and Amy does satisfy that and passes on. So that's a kind of that's a sort of fairly obvious. And map also is fairly obvious. Here comes Bill, and Bill lives in, I can't remember. Bill lives in London. So the output from this intermediate operation, from the previous one, filter doesn't change the type of the stream. This was a stream of person coming in and a stream of person going out. But here, because we're doing a mapping to the city that people live in, the result is a stream of the cities that come out. And the type of the operation, it will usually be a lambda that is going to be used in a map. Is something called a function. It's a function from a person to a city. These, by the way, are in Java 8. Types like this are just ordinary interfaces. There's been a very I don't have time to talk about that tonight, but there's a very nice integration of the idea of lambdas, which are essentially functions expressed in Java, into the existing type system using interfaces. So a function, a person's city, is just an interface. It happens to be in the library, in the Java util function package. Happens to be in the platform library, but it doesn't need to be. You could define one like this yourself. All it needs to do is just have it just needs to have a single abstract method which will apply whatever it is you're interested in. In this case, the getCity method to the first argument to give something of the type of the second argument. No matter what you call it, it just needs to have a single abstract method that does that. So it's very simple. I mean, this idea was I think a great achievement of the Java 8 designers, in that they managed to bring this fairly strong implementation of functional programming into the existing Java type system without having to change it too enormously. Okay, so the next intermediate operation is peek, and I don't have an animation for that. It's just debugging. It allows you to see as the value comes through. It allows you to monitor them as they pass through. We'll see shortly that that's not as straightforward as you would think, particularly because when you come to parallel streams, the order in which values become available is completely is largely indeterminate. The only one that's really worth paying a lot of attention to is flat map, which is always fairly confusing to people first coming into functional programming styles, and because flat map actually breaks down values that are supplied to it. Here we've got a stream of strings coming in. Here's a single value for this a single string coming in. It consists of these characters A, M, and Y, because it's the string Amy, and flat mapped to int. In this case, I chose this because it's the easiest one to demonstrate. The reason it's flat mapped to int is because it's going to produce characters rather than strings. Not a reference type, in other words. But the idea of the flat map is it's now going to take this object and turn this into a stream. So a stream of you get a stream of characters out. So what you get out here now, instead of being each element entering into a flat map operation, results in potentially many elements coming out on the outstream. So those are the intermediate operations. The terminal operations are actually the ones where they're really interested in the Stream API, and in my opinion, I think they're much most interesting. There's some kind of ordinary ones here, which you've already seen some examples of. You saw how you could ask whether all the person objects were adults because any match and all match do something rather obvious with predicates. They test whether a predicate is ever satisfied by any element of the stream or whether it's satisfied by all of them. Find first and find any kind of obviously have similar properties except they're looking for objects satisfied by a predicate. There are some side effecting operations which I'm not very interested in. And reductions form the biggest and most important part of the terminal operations, the way the streams end. And this is really where the whole thing about parallelism comes in, and the necessity of actually being really being functional in the way that the streams are implemented. So one of the a big motivation for the way that streams are implemented came from a talk given by Guy Steele, which you can actually find in various versions on the internet and YouTube and elsewhere. In which his kind of bottom line was of this talk is that the best way to write parallel applications is not to have to think parallelism. So he's trying to think about how to get from imperative languages that require you to explicitly model parallelism to the point where you can essentially have automatic parallelism. What would you need to give up? The question is the question I was asking. What would you need to give up in order not to have to think about parallel, not have to think about parallelism, but just get it free? The talk is in fact entitled "How to Think About Parallel Programming: Not." And it was a strange loop in 2011, but I think there are earlier versions as well. So he puts the idea of developing automatic parallelism into a sequence of historical developments in computing under the general heading of automated resource management. So to start off with, we were writing in machine code. Some of us actually remember writing machine code, believe it or not. And we were really relieved when assemblers came along. Because at least the nice thing about assemblers were you didn't have to remember the physical address of the code. Right? So your code was denoted by symbolically. And if you wanted to do a jump, say, you just provide a label to that jump rather than having to remember where it was. In my early days as a system programmer, I actually had at times, I never wrote in machine code, but we had to write patches for operating system bugs in machine code, and you had to remember exactly the physical address of the operation you were jumping to. Linkers allowed us to forget the relative location of code. Register allocation allowed something that used to be done manually by the programmer, that then was given to the compiler to do, allowed us over which registers sometimes leading in some cases to a big loss of efficiency. So I mean, at all these stages, by the way, and I was there for many of them, you would always get people complaining, "Oh, this will never work because it will always be too inefficient." High-level languages, I can still remember when people say high-level languages will never be as efficient as hand-written assembler. Heap management allows us to get the absolute location of the data. And again, I mean, that's really common still to hear people saying, "Oh, garbage collection's far too expensive. Dynamic runtimes will using garbage collection will never be as efficient as manual heap management." Virtual memory is the same. Well, what is it? Each time we're having to give up control, and potentially we're going to have to give up efficiency. And what we get in return for that is automated features which allow us, most importantly, to lift the level of abstraction of our programming languages and allow us to focus more on the problem that we're trying to solve, on the business problem we're trying to solve. So what do we have to give up to get automatic parallelization? Well, what we're going to have to give up for that, he says, Guy Steele says, is some old habits that are really deeply ingrained. For example, a proxy for efficiency in sequential programs is the operation count. Right? So you typically think more operations I've got, the longer it's going to take. But that may well not be the case for parallel programs, because it's entirely possible that if you can succeed in parallelizing your code, then the fact that you have to have more instructions won't matter because they're executing simultaneously. You may have to be prepared to waste operations to reduce communication. Similarly, minimizing space usage by sharing data between operations is entirely possible something you need to give up because you're going to want again to reduce coupling. Coupling between the different processes in parallel programs is the thing you really have to avoid, because that is the thing that serializes your processes. And anybody who's ever looked at those horrifying graphs you can get very simply from Amdahl's law, they tell you that you have as much as a ridiculously small number, 5% of your program runs in serial. You're basically throwing away the advantage that parallel processes give you large numbers. But here's the killer: linear decomposition. You're not going to be able any longer to process one thing at a time to accumulate results. The reason you're not going to be able to do that is because if you're processing one thing at a time, you're accumulating the results in a single location. You must protect that location by mutual exclusion, and it will get hot. That will be the point of serialization. The big thing that we're really going to have to give up are accumulators. And that's really serious. That looks like a very serious problem. No more accumulators. I mean, we use accumulators all the time in imperative programming. So this is really quite a challenge. No more accumulators at all. We're going to have instead, he says, to go to use divide and conquer algorithms instead, using symmetric merge operations rather than the rather than the linear accumulation algorithms that we've used so far. The major impact of this and the Stream API is on terminal operations. Because terminal operations are essentially in Java accumulation. And the classic thing that you do as a result of a Java program is you accumulate a lot of results in a collection. That's normally what we do, and these collections are of course mutable. I mean, Java is not a functional language. It's certainly not going to become a functional language in the sense that we're going to somehow accumulate all these results functionally. That's not going to happen. We're going to be continuing to write to we're going to be continuing to add them into mutable collections. So they actually had to invent the innovation, the biggest innovation, I think, in the Stream API was the invention of this idea of mutable reduction, which sounds like a contradiction in terms of functional programmers, but actually turns out to be a generalization of reduction and to be So I don't need to talk very much about this because the groundwork is laid for me by Michael's talk. Here's a simple example. Here's linear accumulation. If you want to just add up the elements of an array, as I'm doing here, the code that we have to stop using if we want to be able to parallelize effectively is this, because what this is saying is I'm going to have to repeatedly increment sum, and if I want to execute this code for different areas of the array, if I want to execute it using different threads, I'm going to have to use synchronize or some other Java synchronization primitive in order to prevent corruption and destructive interference by the threads. And once I do that, then I'm throwing away the advantage of running in parallel at all. Instead, what I'm going to need is something which looks actually remarkably like a monoid, I would say. Not necessarily a monoid. The in-stream interface has actually two versions of reduce, which in this case you're actually, I believe you're making a monoid. In this case it simply must be an associative operation, which I'm happy I don't have to explain now. Thank you. And the way that's going to work is that instead of having a single location into which the results are going to be accumulated, what instead we have here is reduce is going to work on a function. The one that here is called an in-binary operator. Just another one of these interfaces in Java util function. It's going to, in this case, it's the one that simply takes two values and returns their sum. Why is this different? Well, the reason why it's different is because you can apply it to any pair of values in the array, or you can apply it to a computed value and another one. So this execution tree looks like the one that you saw on the previous slide, but because this is an associative operation, which I don't have to explain now, this execution tree is just as valid. That's what associativity gives you, and the result of that means, of course, now you can see that on a broader scale, we could break this array up, and we could say, well, we're going to give each one of the segments of the array, we're going to give to a different thread, and then we can combine the results that are computed by these threads in dynamically, in a symmetric way, without having to use a single location for this. So this is really this is the kind of the key advance to seeing how we can change from using an accumulator into a reduction style operation which avoids all of that. And this works actually fine for primitives, and it works fine for immutable objects, and it's exactly what functional programmers classically would recognize. So here's here's an example of how it works for primitives. In this case, we actually have created a monoid. Here's the identity operation, and here's the here's a single thread using the addition binary operator for addition, and here they're being combined also with the binary operator for addition. So that works fine for primitives, and the question is, and it also works for immutable objects, but the question is, what are you going to do about the thing that we really want to do something about, which is mutable objects? Because what we want to do is, this kind of thing is okay, but it's really, in Java terms, this kind of thing is toy. These are toy programs. What we really want to do is we want to be able to accumulate values into lists and sets and so forth, because that's how things work. It's quite interesting. If you look at the Stream API, you see that, in fact, the designers of the Stream API didn't understand the problem I'm about to tell you until very late in the day. So actually, they really do allow. There's a reduction. There are reduction operations which really do take mutable objects in this kind of way. Is this going to work? I don't know. Can anybody tell me whether that's going to work or not? There's a fatal flaw to this way of doing things. The fatal flaw is that because it's kind of late in the evening, and I know the pub calls on that, so I won't push you on this. The fatal flaw is that reduction assumes immutability, and this object here, this empty list, an identity is assumed to be reusable. Right? So if you can repeatedly, it will be repeatedly reused by different threads, and the result will be that you'll actually get partial results will be accumulated by other threads. And so this really didn't work. It turned out to be really a bad idea. You can do it, but it was a mistake in the API. They ran out of time to take it out when they realized the mistake. Here's the way that you should do it, and of course this is the way. This is actually the standard way of doing it in the Stream API, and that is to take not an identity collection, but a supplier, which is a function that takes nothing and gives you an empty, typically an empty collection. Sorry. So if that's what gets called each time you want to start a new reduction, then you'll always start with a fresh one. So the three parts of a collector, then, the thing that does this mutable reduction, are the supplier, which gives you the empty part, and an accumulator, which will add a single element to typically to a list or to a set or whatever it is, and then a combiner, which puts two of them together. In Java, that would be that's typically the add-all operation for like a list of sets. Collection has an add-all. Here is what corresponds to what I showed for addition before. So it's complicated, and Brian gets told me that I must never show people this because it put everyone off, and they think that you have to define all this stuff every time you just want to have a stream that feeds into a collection. But I like to tell people this because then you can see how clever the designers were, and also what foresight they had in actually supplying a whole bunch of predefined, which will do all that work for you. You don't have to think that out. I just think it's nice to know what's going on behind the scenes. So you've got collectors that will take your values coming down the stream and dump them into a list or into a set or into a map, or will concatenate strings together. The framework provides the supplier. So you get array list and you get hash set, whatever. If those defaults are going to be good enough for you, you can supply your own. You can decide for yourself what supplier you want to put them into. So if you want to put them into a navigable set rather than a hash set, you can say you can use the that's created by this. By that factory method. And there are some more complicated things which produce classification maps that are really very cool. Very cool. And my note here says they cover 99.9% of your needs, but actually I think it's probably more than that. These collectors are all produced from factory methods in the collectors class. Collectors class is quite confusing when you first see it because it's got so many of these predefined collectors. You think, do I have to learn all this? And it looks like it's going to be tough for you, but actually the way you see it, when you see these, is, oh, look what they've given me, rather than this is what I have to learn, but how generous of them to have provided me with all of this. So I'll just show you briefly how a couple of collectors work. We've now got to the end of the life cycles for streams. Started off with the splitterator, went on to the intermediate operations. Now we're on the terminal operations, the things that actually pull the values down the list. So if I say I want to generate a stream from this collection, and then I say now I want to collect it into using this collector, the one that's used by this factory method on that utility class, then the result of calling collect will pull the values from the list through the stream and into that. And the way that it works is this: you've got here comes a value. When the collector is going to create a set, because this is a two set, it will create a set, actually a hash set in practice, and it'll put the different values into that. And then when the stream is exhausted, at the point when all the values in the splitterator have been used, then at that point it emits the set you were looking for. So that's how to set and to list. This is how to map works. So this is something slightly different. In this case, what we want to do is we want to make a mapping from the city, from each city to in this case a list. We're going to get to the person. This is to map to the person who lives in that city. So the idea of this is that we're going to the first function will be applied. The first function will be applied to produce the key of the map. The second function will be used to provide the value in the map. So a reasonable question would be, what if there's more than one? What if there's more than one value for a given key? And the answer to that question is, if you use this overload, the one that I've just shown you. I've gone back too far, sorry. If you use the overload that I've just shown you, then you will get an exception. So there's a clash there. And there's another overload which provides a binary function which tells you how to combine the two value elements if you get more than one. Right. So I think I should speed up because we're clearly getting towards the end of we're getting into pub time. Let me think. Grouping by, I kind of like grouping by, but I think I'm going to miss that out. Because there's a lot of that, isn't there? Concurrent collection. So concurrent collection is really this is really a major innovation of the Stream API, because what it allows you to do is to specify that you want your stream to be executed in parallel, even though the results are going to be accumulated into a non-threaded container. So you can say all you need to do in order to be able to run one of these streams in parallel is simply call an intermediate operation called parallel. It's really as simple as that. To get good performance out of it is a different. But the manifesto for introducing parallelism to streams was supposed to be would be explicit and unobtrusive, and it is explicit. You have to say parallel, but it is completely unobtrusive. It turns out that actually to get an improvement in performance is a different matter, and one that I don't have time to talk about now. But they did make sure that there's a very, very strong emphasis in the design of the Stream API that says that nothing that you do, no result that you get, if you're running sequentially, should be changed if you decide to run in parallel. In other words, that as far as they're concerned, whether you run sequentially or parallel is an implementation detail. Right? It's sort of like choosing between different implementations of the list interface. You may get performance differences, but functionally it will produce the same thing. And that's pretty smart when you consider, for example, you're going to need to be able to you're going to need to be able to take the values coming from a parallel stream where the elements are being evaluated by different threads and still put them back into something like array list or hash set. So that's pretty smart. It comes at a price because obviously the framework has to manage has to manage thread-safe accumulation of these containers. So if you have a container, and this is a very common case, you have a container that's already thread-safe. Say for example, nowadays increasingly lots of serious Java programs use concurrent map implementations. That gives you the opportunity of the framework allows you to say, you don't have to manage this for me. My collection I'm dumping into will manage this. So instead of to map and grouping by, you can get to concurrent map and grouping by concurrent. Okay, so that's concurrent collection. I'll skip over writing a collector because we're clearly not going to do that today. And just a little bit more about parallel streams. I think we've probably got the idea about split operators already. The idea of a split operator is to break down a splittable data source. And notionally, this is what split operator does. These brackets here represent the part of the data structure that is covered by a split operator. So the split operator will, if it can do it, say supposing it's something sufficiently splittable like an array list, it will split it. It'll actually assign the top half of the data to a new split operator that gets created, and it will give itself a set at the bottom half. And then this will happen repeatedly until you down to typically down to the number of cores that you have available. A split operator will check this with the operating system to find out how many there are. And then each one of the resulting segments is available for execution sequentially by an individual thread. So that I hope covers gives you some sort of sense in a very condensed way of the life cycle of a stream. The source of a split if it's going to be evaluated in parallel, just iterated over, it's going to be evaluated sequentially. The intermediate operations I've talked about, and I've tried to give you some sort of sense of what's going on with the terminal operations. We want to talk about visualizing parallel streams. Well, yeah, visualizing parallel streams, it's worth talking about this for a moment, because sometimes it's quite hard to understand why there are such limitations on many of the operations on streams. So for example, there is no implementation in Java 8 of an operation which says evaluate until I get a certain value. You can't have a poison pill in a stream. You might wonder why on earth not, because that's like a really obvious thing to want to do, isn't it? I mean, I'm just going to keep on getting values from this down the stream until I get the one that I'm prepared to stop on. And that one's at that point when I know the job is completed. When you think about how parallel streams are actually evaluated, each one by a different thread, after the split operator has broken them down, you see that actually determining when you get the first occurrence of a certain value is not at all obvious. So they may actually be evaluated in some completely random order. I've just chosen something really fairly random here to indicate that if we're looking for a particular value at a particular point, we have no way of knowing. We certainly would know if it came in the right order on that stream or on that one. Between them, there's no synchronization. And that's really important not to have the synchronization, because if you're required to have synchronization between the different streams, then of course you're actually losing, you're serializing your code, and you're losing the advantage of running parallel. So this brings me really to the end of the focus of this talk, which was about parallel readiness. So a big message of Stream API is that sequential execution is no longer we should no longer be regarding it as the default for how programs execute. In practice, it is currently still for very many problem domains and on lots of hardware. But going forward, if you think about that, the automated resource management list that I showed you earlier on, you see how over time the idea of relinquishing control over the various aspects, things like absolute location code, absolute location data, and so on, have finally are now really just kind of part of our culture. That's the way that also the control over order of processing is going to go as well. So sequential execution is no longer the default, and over time we will just come to take that for granted as well. In the same way as we take it for granted that we don't know where our data is exactly in memory. Sequential execution is still usually more efficient. I've become more pessimistic as time's gone by about the practicality of parallel execution in today's world. But I haven't relinquished the idea that over time they're going to discover more. They're going to discover increasingly useful ways of parallelizing, of automatically parallelizing code. And you're making your code parallel ready. You're future-proof if you follow pretty simple rules. So if your code has to be agnostic about its execution mode, if you use the Stream API, you can guarantee if you program according to the guidelines of the Stream API, then you have future-proof code in that sense, because operations in the Stream API have equivalent effect whether they're executed sequentially or parallel. If they're non-deterministic, they'll be equally non-deterministic. If they're deterministic, they'll be equally deterministic. So we're really decoupling the mode of execution from the functional behavior, pretty much in the way that, as I said, we do with interface implementations. So parallel ready is not only about parallel execution. It is about parallel execution, but we believe that we've basically got diverted into a model of programming which has just tied us to sequential execution for no very good reason. And we think that a lot of time actually writing code in an agnostic mode. So if we're careful to ensure that it can execute in either mode, we think we get better code out of it. Is your code parallel ready? Well, obviously it isn't, because we're all, as Brian says, we've all got our heads stuck in the sewer of sequential programming. But the Stream API provides a framework and a lot of support for writing parallel code. You just need to cooperate with it. Depends on you behaving in a fairly same way. The Stream API, the Java for Java util stream, specifies what it means by stateless behavior. So for example, you can't have behavioral parameters. Those are the intermediate operations. Can't depend on their history, for example. Because if they depended on they might be influenced by what's happening in another thread. So if the result depends on any state which might change during the execution of the stream pipeline, then you're assuming sequentiality. You can't modify a stream's data source during execution unless it's thread-safe class. Don't rely on side effects, sure. If you do that, then again you're assuming sequentiality. The Stream API offers a framework. So the result is then what we get with the Stream API is a framework that will change the way that we're going to program bulk operations on data. Up until now, the model for bulk operation has been iteration over collections. The style is going to change in Java 8 from that to stream processing. We believe that that's going to produce a better, not only more functional and more readable and more maintainable and more finely grained style of programming. But we also think that the idea of writing in a parallel ready style future-proofs your code against the changes in hardware that's certainly going to come up. So all we have to do then is actually internalize the lessons of the Stream API and cooperate with the constraints, not regard them as something that's actually imprisoning us, but regard them instead as something that's liberating us. And you can do that today. You can do it tomorrow if you're not going to get onto Java 8 till then. But certainly you don't have to wait until we're all running on massively powerful hardware. The future programming is available to you pretty much now. Thank you very much.
We have time for maybe a couple of questions if we're quick. Or we can go straight to the pub.
It's 9 o'clock.
It's 9 o'clock. Okay, so I think we're going to head to the Grange, which is just around the corner. Maybe a meal for a bit first to do a quick tidy up, so hopefully see you all there. And say thank you once again to all our speakers. Maybe another round of applause. And thank you all for coming. This is actually the first time we've ever finished all the pizza at one of these events. So maybe we just didn't buy enough of it, but okay, I'll hopefully see you all shortly.